Okay, Shwana. So let's start with this. See, we have completed till the graphs part. Last part that we did was the graphical portion of insulators and semiconductors, and I told you the graph of alloys and conductors also. Now, very small portion is left, terminal potential difference. Let us continue with that. Terminal potential difference, internal resistance, and potential, the electromotive force, EMF. These are the three terms that we'll be talking about today. So it's a very easy portion. Basically, let's discuss what is internal resistance. See, this is how you see a cell. In real life, this is how you see a cell, and this is how you draw it in the circuit. So when you open the cell, cut through the cell, and see the segment of the cell, in your electrochemistry, in chemistry, you must have studied, this is how the structure of the electrolytic cell is present. The anodes and cathodes are dipped into the electrolytic solution where ions are present. So the positive ions get attracted towards the anode and the electrons get attracted towards the cathode. So these electrodes are dipped within the electrolytic solution. Now what happens is, within the cell, see, if electrons are present and these positive charges are present within the electrolytic solution, right? So these electrons in electrolytic solution, these are present here. What will happen? The way the normal resistance occurs within the wire conductor, when electrons are flowing through the wire, when the electrons are drifting in the current carrying wire, what happens is it always feels an opposition or resistance to the flow of its motion, which we call as resistance. We have seen also the different formula of resistance. We have seen the numericals also on resistance, and we know what is resistance. So if that same resistance is felt in the motion of the electron when they are moving or they are colliding among themselves or with these positive ions, there is a resistance felt by the electrolytic solution as well as the electrodes. So these electrodes and this electrolytic solution, this offers some resistance or opposition to the flow of electrons. This is called as internal resistance, because see, this is how you draw your cell. This is how it actually looks like. Within this process is occurring. So that's why we say internal resistance. And always draw a small resistor beside the cell to show the internal resistance of the cell, and you'll also find the internal resistance of the cell drawn in that manner. So resistance offered by the electrodes and electrolytic solution of the cell is called the internal resistance. Am I clear? Okay. Write down this part, make the heading internal resistance, then I'll start with EMF. Okay, coming to the electromotive force. So see, this is a misnomer. If you see the term, this appears as force. It's not a force. It's the potential. It's the voltage that you've been studying since chapter 2. Okay, so electromotive force basically means the potential only, EMF that we say. So it's the maximum potential difference that occurs within the terminals of a cell in an open circuit. Now, open circuit means this. All right. Now, how to calculate the EMF? You calculate the EMF by taking the voltage of the higher side minus the voltage at the lower side. So if this is given, still you will take this. Even if this is the figure, you will take this. How do you identify which terminal is higher? The longer one represents the higher terminal and the shorter one represents the lesser terminal, lesser voltage. Now, what's the difference between the terminal potential difference and an EMF? So basically, you can remember this EMF occurs within the internal resistance. The potential difference of the internal resistance will be given by the EMF, whereas the potential difference across the external resistor will be given by the terminal potential difference. Or you can simply say that terminal potential difference is the potential difference that occurs in a closed circuit. So just the opposite of EMF is your terminal potential difference. So potential difference across terminals of the cell in a closed circuit or external resistor. I think it will be better if you remember it through the external resistor and internal resistor, because in the numericals, you will get the circuit diagrams and there you have to identify. And definitions also come. So this is how the circuit appears. This is the terminal potential difference across the external resistor. And see, this is the internal resistance that I have drawn with just beside the cell, so as to represent the internal resistance of the circuit. This is different. This is your external. This is your internal. And see, the voltage of the cell of the internal resistor. See, I have written it as E. E means EMF. And here, whatever will be the voltage, that will be then considered as the terminal potential difference. Are you getting this, Shwana? Are you able to differentiate between terminal potential difference and the EMF? Okay, Shwana. Coming to its formula also. Formula is very easy. We have seen Ohm's law. What was Ohm's law? V is equal to IR. Now, what is resistance here? Resistance is basically the total resistance present will be your internal and external. This is the external resistance. This is your internal resistance. So how will you get the total resistance? You will simply add it. So R plus small r, capital R plus small r will give you the total resistances. So your current is equal to EMF divided by capital R plus small r. Why? Because this is because of this Ohm's law. Okay, this is because of the Ohm's law. Now, if I say V is equal to IR, and I have already got the value of I as E by R plus R, I can substitute this value over here. So V is equal to IR. So I is E by R plus R. So this is V is equal to IR. Right. So if you want, you can write this as ER by R plus R, or even you can put it like this because you have a formula. You have a formula to put over here. Now, what is the actual formula that you will be using? The problem is that you are having the internal resistances potential also, and you're having the circuits potential also. So when you write the equation, the entire equation becomes V is equal to E minus IR. It can be E plus IR also. That case I'll explain you when you have to use E plus IR or E minus IR. Best way now to remember this, Shwana, is that see, what is the potential differences formula according to Ohm's law? V is equal to IR, right? This is the basic simple formula. V is equal to IR. That's it. Now, if I say what is the potential for the internal resistance, you can say V is equal to I into small r. Resistance of internal resistor is small r. Current is the current that is flowing is I. So resistance, the potential of the smaller resistor or the internal resistor would be I into small r. If I ask you what about the external resistor, then you will say I into capital R, because capital R is the resistance for the external resistor. So I into small r is for the internal resistances potential. I into capital R is for the external resistances potential, right? Now you have I small r, I capital R. That's it. This also comes separately. This you should know. Now, if I ask you the net potential difference, so one potential was across the cell. So I have written it as this. Other potential that was across the cell, which we have calculated, is I into small r. That's why this is the formula, E minus IR. But apart from this, these two formula can also be used when you are just asked to write the potential of the internal resistor. So use this formula. If you know the current, if you know the what's the internal resistance, simply use this formula. If you know what's the external resistor, see, external resistor is sometimes not just given as it is. Sometimes you need to calculate it. When you have multiple resistors connected, you have to identify the series and parallel combination and then deduce the whole circuit into one final R equivalent, which will be acting as your external resistor. So it's not necessary that you'll always get just one simple external resistor connected. No, you can get multiple external resistors connected, but you have to reduce them and get your resultant or equivalent resistance. And then you can simply multiply it with the current to get the resistance, the potential. So we use V is equal to IR for that. Are these formula clear to you? See, this is the question. You write down this question, try this question. First, write down all these things. Then I'll discuss it. I'll show you the solution also. We'll discuss it also. Please start writing from EMF. Can I write down this question? Okay, Shwana, let me discuss it then. See, we can clearly see this is our external resistance that is given. And this is the EMF, 22 volt. And see, besides it, we have the internal resistance. So if you have to get the current, very easy, E divided by R plus R. So 22 by 10 plus 1, 22 by 11, that is simply 2 amperes. Now, potential difference across external resistor. So we'll say I into capital R, that is 10 we will use. See, current is 2 amperes, 2 into 10 ohm. So that will give us 20. And volt potential difference across internal resistor. So 2 into 1, that is 2 volt. See, when you add it, you're getting your 22 volt back. So it means we have done the calculations correctly. And terminal potential difference is EMF minus IR. So very easy. It will be just your 20. 22 minus 2, it is 21. Now, I was telling you, if you see the current is going out from the positive terminal, entering into the negative terminal, normally, this is what happens usually. So we use this equation, V is equal to E minus IR. But in this case, Joanna, if you see the current is coming from the negative terminal and is terminating into the positive terminal, then we use the equation V is equal to E plus IR. Okay, so this is, be careful if you have this case. Okay, write down till here. And one more thing, see, if key is open means no current means no voltage. So this is what you can just recall whenever you have zero current. Write it, then we'll discuss something else. I'll discuss series and parallel combination. Firstly, let us see the series and parallel combination of the cells. Now, if you have cells, see, resistors are different. Their resistors also have their series and parallel combination. Like right now, I'm talking about the combination of cells. Now, Shwana, just remember one thing. If the cells are arranged in the same order like this, you add all the EMFs. Resistance will in any ways be added always because you cannot have a negative resistance. But if you see a cell is put in a reversed order, like this, then whichever cell is put in the reversed order, like see, this is the pattern, smaller on the right, higher on the left, smaller on the right, higher on the left. This one is an opposite. So which one ever is connected in reverse, you put it as negative. So just put a negative sign. One question I'll show you in between. See, plus, minus, plus, minus, plus, minus, all are connected together. So if you have to get the current, for current, we now require equivalent EMF because with so many EMFs, how will you get the current? So equal EMFs means add all the EMFs. 15 plus 5 plus 10, that is 30 volt. What's the internal resistance? 2 plus 2 plus 1, that is 5. So now you put it in the main formula of current, 30 by 10 plus 55, that is 30 by 15, which is equal to 2 amperes. And second part says terminal potential difference across 10 volts. So that is I into 10. What is the current? Or what you can do is you can use this full big formula also. I minus E minus IR. E is 30 minus what is I into R? 2 into 5, that is 10. So 30 minus 10 is 20. Is this clear? How to utilize this formula? Shwana, is it clear? Yeah, you've understood, Shwana? Are you there? Okay, Shwana. Write it till here. Write it till the reversing of cell. Then I'll start with the resistors series and parallel combination. Okay, look, this is the series combination. So let's just quickly see the series and parallel combination. That is what is just left. Shwana, one thing before I conclude the class. Shwana, do you need any extra classes or do you need more classes? Or any other chapter you want to complete or you want to revise anything? Please text me. Okay, Shwana. So I think tomorrow we won't have our class then, because right now this current electricity's revision will be done. If you want any chapter to be revised, anything, you can just tell me. Okay, so tomorrow I think we don't need any class. Okay, okay. So let's complete this. So in series combination, see, current through each resistor is same when the voltage divides. So in series combination, you have to see your current is going to remain the same and voltage is going to divide. Now see, when you add all the potentials, V1, V2, V3, V4 till Vnth, you add all the potentials, that will give you the total potential of the circuit, because individual potentials are different, right? Since individual potentials are different, that's why we can use the formula of Ohm's law. But what is the same? The current is going to remain the same. So IR equivalent is equal to IR1 plus IR2 plus IR3 up till IR nth. N means number of resistors which are connected. Your current will be cancelled. Equivalent resistances R1 plus R2 plus R3 up till R nth. Okay, you have to remember that. If you see, we did potential and capacitance also. Same thing like the capacitor and the combinations of the capacitor. Difference arises in the formula. In the capacitor, the parallel combination had such direct addition of all the capacitances. If you remember, there we had in the parallel combination of capacitors C1 plus C2 plus C3 up till Cn. Here in series combination, we have the total addition of all the resistors like R1 plus R2 plus R3 up till Rnth. So if you have to calculate the current through each resistor, it will be I only, because current is not going to change, but voltage is going to be different. So whatever is the current of the circuit, just multiply it with the respective resistance, you will get the voltage of that particular resistor. For the total voltage, you require the total resistance. But for the individual voltages, just take the individual circuits. And sometimes power dissipated across each resistor is also mentioned. So see, you have the formula P is equal to V square by R, but it's better in the series combination if you use the formula I into R, I square R, not I into R, sorry, I square R. Okay, there will be a 2 also. Why? Because current is going to remain the same in this circuit. So this will be beneficial. Okay. And see, like this is a very easy question. 5 ohm resistor, 10 ohm resistor, and you have 10 voltage battery here. R equivalent, see, they are in series. Simply you are going to add it. 10 plus 5, 15 ohms. Total voltage is already mentioned, 10 volt. Total current, see, we have the total resistance now 15 ohm. Total voltage is 10 volt. So total current will be what? Voltage by the total current is going to be voltage into voltage by the resistance, that is 2 by 3, 10 by 15 or 2 by 3. Now, voltage across each. So what did I tell you? Take the current and multiply it with the resistor of that respective resistor. Like 5 into I, 10 into I. So this is how you are going to get the current. See? 2 by 3 is the current into 5, that is 10 by 3. 2 by 3 into resistance, that is 10, like this. And you can check also 10 by 3 plus 20 by 3 is giving you your 10 voltage back, means the voltage distribution is right. And then it asked us to calculate the individual currents. Individual currents are not going to be different. They are going to be the same current as that of the circuit, that is 2 by 3 amperes. Is the series combination clear to you? Okay, Shwana, please write it from here. Okay, last part, Shwana, coming to the parallel combination. So see, in parallel combination, your voltages will remain the same, current will be different. So when you take the formula, V by R, V by R, V by R, all the potentials will be cancelled. You will get the resistance as reciprocal addition of all the resistors, okay? Please write this also and just text me done. Tayyiba, please join after 5 minutes. Okay, Tayyiba, please join after 5 minutes.
Okay, ma'am.
Okay, Shwana, you've completed? Okay. Then thank you, Shwana. If you have any queries, if you want to conduct any class, please let me know.